Hey everybody, I'm just going to wait one more minute to let people show up. I've started recording this meeting already, so just to let you know. Okay, everybody, I guess we'll get started.
建议为每位空巢老人办身份卡。哎呀，别空巢老人了，什么空巢人办身份卡得了，我也空巢啊。
Hey, Yang. Oh, there you go. Good, thanks. Right. Okay. The topic of today's talk is computational complexity. There's supposed to be a notebook for this week, but I haven't managed to get it done yet. So I'll post it as soon as it gets done, which will probably be Friday. Sorry about that. It's a lot of work for me when I have quizzes in a week, and I have 2 this week, mostly because it's all online, and I have to make multiple versions of every question. So it takes quite a long time to do. You have an assignment that's been released. There was a correction to the assignment. Question 4, the example output was wrong. That's been fixed now. If you already finished question 4, and I know some of you have, you'll have to go back and adjust your answer so that it actually meets what the question was asking for to begin with. So, okay. And don't forget you have a quiz tomorrow. It'll be similar. Can we go over question 4? I'm having difficulty with the inductive step if statement. Amelia, sure, we can do. We can look at question 4. Yeah, let's do that now. Why not? That's fine. Let me just pull up question 4 for everybody who hasn't seen, because I'm sure a lot of people haven't seen it yet. Get rid of Reddit. Here we go. Okay, question 4. Let's make it a little bigger for you. I hope. Where's how come it's not? Oh, that's interesting. Oh, there we go. Okay. Okay, so question 4 is basically asking you to write a function, a recursive function, that computes the next power of 2, right? So you want to compute the exponent p, so that 2 to the p is bigger than or equal to the input value n. Right, but you want the smallest value of p, right? So over here, if you ask for the next power that's bigger, next power of 2 that's bigger than 0, return 0, because 2 to the 0 is 1, and 1 is bigger than 0, right? Similarly, 2 to the 0 is equal to 1, so that's good. 2 to the 1 is equal to 2, right? 2 to the 2 is equal to 4, which is bigger than 3. Right, and it's the smallest power of 2 that's bigger than 3. Right, and similarly, let's see, 8. So 2 to the 3 is equal to 8. Right, and so you want the right. Sorry, 2 to the 4 is 16, which is bigger than 9. Right, and it's the smallest value of p. That if you raise 2 to the power of p, it's bigger than 9. Okay, so the I think there's a hint, right? So the hint says consider using repeated floor division. Right, so the idea is you're basically going to take your number, that, right? You might have to do something with it, so we'll work through what you have to do with it. You're going to divide by, and then in the recursive call, you're going to divide by 2 each time, right? So you're going to have that value, and you're going to use floor division because everything here is integer math, right? So you don't care about the decimal part of the answer. You'll see why, I hope, in a minute. Okay, so if you look at the table of outputs, what does the question say? Oh, actually, it doesn't. 2 to the p is greater than or equal to. Yeah, so you don't have to really worry about. Well, for negative values of n, this thing on the thing on the. How come I can't select? The thing on the left-hand side, 2 to the p is never negative. So for any, you don't really have to worry about negative values of n because that's just going to fall into a base case. If you look at the table, right? You remember, so, oh, I should back up a step. So in a recursive, when you formulate a recursive algorithm, you're always concerned about the quote unquote size of the problem, right? This function only has one input, right? So the size of the problem happens to be the value of n, right? So it's not difficult to determine what the size of this problem is, right? It's equal to the value n. And so remember that in the recursive, in a recursive function, you want to constantly reduce the size of the problem until you reach a base case. So if you look at the table here, it's obvious what the base cases are, right? The base cases are here, right? Whenever the value of n is 0 or 1, right? Or in other words, whenever it's less than 2. So we can, if you're going to cook up your recursive function, you can just start with that right away, right? So this one's not terribly hard to find the base case for. So let's pull up idle. Sorry, I just want a new editor. Okay, so we're gonna, so you would do this in A3, right? So if you have the assignment, you'd be editing A3.py, you would just define your function, and I think it's, yeah, so next how2. Right, so this is already in A3 for you because I gave you a little bit of starter code. We know the base cases, right? So the base case is just if n is less than 2. So if n is less than 2, we know the answer is 0, right? I think in most of the examples, I've been putting in an else statement for the recursive part. You don't have to put it here if you don't want to. If you leave it out, it's fine because you're going to return, the if part returns 0 anyway. So whether or not the else part is here is not important. I think the textbook leaves it out, and I tend to put it in. Doesn't matter either way, right? You just, as long as your base cases are exhaustive and in the right order, everything will be fine. Okay, in the recursive case, it says consider using repeated division, right? So consider using repeated division. Okay, so for the value 2, right, we don't have a base case. If I take the 2 and divide it by 2, though, I get 1. Right, so you're in your recursive call, it's going to be something like next pow2, next pow2, and then the question says, look, consider using repeated division. So you're going to take n and divide it by 2, right? Why don't I write that down because it might be easier if you can see it. Come here. Okay, so I'm going to do something like, I want to call, let's do temp equals next pow2, and then using the hint, you're going to do something like this, right? Okay, so, sorry. Okay, so if n is 2, then that's a little better. If n is 2, then next pow2 n divided by 2 is going to be next pow2 1, right? So I'm going to get 0. And that suggests that, right, so that's going to be 0. Okay, let's try 2. Sorry, let's try 2, 3. Right, let's try 3. So if I take n, did we go over question 1? Yeah, if I take n divided by 2 using int division, right? Sorry, floor division in Python. You're going to get 3 divided by 2, which is 1, right? So it's 1.5, get rid of the decimal, so it's 1. And so you're going to fall into this case here, right? So it looks like if you do this, I have to add 1 here to get that answer. I have to add 2 here, right? And if you keep on going, you're gonna see a pattern, right? The pattern you'll see is that if I compute that like this, right, it works. So if I take next pow, it almost works. Sorry, next pow n divided by 2. So that's 4 divided by 2 is 2. Assuming I got this one right, then I know that the answer is 1 plus 10, right? So it looks like the answer is something like 1 plus 10. It's not quite that. You'll see why in a second. I'm just gonna save this. Sorry, computer's a little sluggish today. Why does it want to save? I'm just going to save it on the desktop for now. What do we call this? I guess we'll just call this next copy. Okay, and then I'm just going to test it inside the file itself. So I'm just going to print next cow2. Well, let's do it this way. Oh, let's write a little loop. So for in range 0 to let's do 9. I'm going to print I followed by I, and then I'm going to print the value of next cow2. And run that. So I'm just going to compute. I'm just going to run the function for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, and you're going to get 0, 0. Let's see what we get here. So 0, 0. So these two are good. Right. Then I get a 1, which is right, and then I get a 1, which is wrong. Right. That's correct. Right. That's wrong. That's wrong. That's wrong. It's off by 1. Right. That one's correct. Right. This one's off by 1. Right. So your recursive case here is not quite correct. Yeah, this one's almost correct. It's not quite correct. And this is, well, I'll tell you, this is correct. The problem is in the recursive call. So there's something wrong with that argument. It's not quite right. I'm not going to tell you what the answer is because it is useful if you puzzle it out. It's not terribly difficult to get the correct recursive call. That's almost it, though. Right? That's almost it. Amelia, does that help? Okay, great. Ethan wants me to look at question 1, which we can do. That's no problem. Question
before
one.
You go to question one, Professor.
Yeah. Question 1 is the zipper question, right? This is the zipper question, and you want to you want to use a helper function, right? Okay. So if you read the notebooks, the notebook for last week tells you or explains why you sometimes, well, not sometimes, you often want a helper function. And the reason you want a helper function is because when you're solving a recursive problem, often there's information that you need to use that wasn't necessarily available to you in the original function. So in zipper, right? So basically zipper takes 2 strings and it just interleaves the character of 2 strings, right? And both strings have the same length. So in the original zipper problem, right, you just want to pass in the 2 strings, right? So I want the user of the function to just be able to say, here are the 2 strings, return the zipper of the 2 strings, right? Towers of Hanoi. Yeah, the textbook explanation of the Towers of Hanoi is a little confusing. Let me get through the zipper problem first. So in this, right. Now, if you try to write a recursive helper function where you don't slice, right? So in this solution, I'm slicing the strings. I don't want to slice the strings if I don't have to, because every time you slice a string, you produce a new string, right? And producing the new string here, right? So basically, I'm computing the new string where it's the original string S missing the first character, right? So all I'm doing is taking 1 character off of S, right? But that builds a new string every time, or creates a new string every time, and that's wasteful, right? So you're wasting time and memory that you don't have to, because the original string S had everything you needed in it anyway. So the other way to write this is to use an index, right? And I'm just going to plunk it in here. You shouldn't do this, but I don't want to make another file. So the question says, make a helper function for zipper and have the original zipper function called a helper function. So typically what it looks like is for this particular problem, it ends up looking something like this. Zipper. In the notebooks, I call the helper functions with the name of the original function, followed by _ IMPL. So that's just the zipper implementation. So this is the recursive implementation of zipper. You could call it helper if you want to, that's fine. So we'll just call it st, and I'm going to pass in 0, and you'll see why I pass in 0 in a second. So then you make your helper function, st and I. So in my helper function, let me call it index. So in the helper function, index is the index of the strings s and t. G, so basically what I want to do is I want to start at the front of s and t, right? Because I want to take the first letter of s, I want to take the first letter of t, I want to stick them together, right? And then I want to go to the second letter in s and the second letter in t, right? And then stick them together. And then do the same thing for the third and the fourth and so on. So I'm starting at 0, right? The reason you make the helper function is because whoever is using zipper doesn't really care about this index, right? You shouldn't force the caller to pass in an index because all they care about is zipping s and t, right? They don't care that they're starting at the first character or something like that, but they want to zipper the whole string. And so we've got the helper function here that does the actual work, and it's the helper function that's actually recursive. Okay, so we need a base case, right? Up here, the original base case says if the length of s is equal to 0, right? In other words, if the string is empty, there's nothing to do, right? Just return the empty string. So we can't quite do that here, right? Because we have an index now, right? We're not changing s and t every time. We're just going to change the index. And so basically, the condition is, okay, so when have I processed all of the letters in the string, right? What is the value of the index? Well, the value of the index after I've processed all the characters in the string will be equal to the length of the string, right? So if the index is equal to the length of s, right? You don't care about t in this case because you're told s and t have the same length in the first question, right? So if the index is equal to the length of s, I know that there's no other character left in s, right? So I'm done. So I can just return the empty string. Otherwise, I need to take the first character of the string of s and the first character of t and stick them together. So I'm going to call that the prefix, right? So that's s0 plus t0, right? So you can do it that way. And then I need to compute the rest of the string, right? Well, the rest of the string is just the zipper of everything else in s and everything else in t, right? So the so the rest is equal to zipper helper st and now I plus 1, right? So the rest of the string starting at the next index. That's how you read this. Right? So I want to zipper s and t starting at the next index, right? So when I call it the first time, it's 0, so this will be 1, right? When the recursive call runs, this will become 2. When the recursive call runs, that'll become 3, and so on and so on and so on, right? Oh, hey, did I just answer the question? Yeah, I just did the whole question for you. Oh, there you go. Everybody should get perfect on the first question. Okay, so if you test this out, it'll work. I'm pretty sure it'll work. Right. So there's question 1 for you. How many questions? There's 8. Right. So everybody should get 12.5% right away. And that's how you solve zipper. Right. Okay. Towers of Hanoi. Okay. So there has been some conversation about this. Zachary is saying that he understands how it works, but the textbook example is confusing. I think. Oh, I don't have it handy. Zach, so I actually have PowerPoint that actually shows you how to think about the towers of Hanoi problem recursively. Is it okay if I post the PowerPoint to OnQ and not try to dig it up now? Because I have to, I actually have to get it from somewhere. So Zach, is that all right with you if I post the PowerPoint? Maybe do a little video for you? You still there, Zach? Okay, great. Let me do it that way. I think it'll be easier if I do it that way. And then, yeah, and then everybody can see it. You don't have to watch me fart around trying to find this file. Okay, I would like to talk about the actual. I guess it's basically going to be a lecture today. You can see there's quite a lot of slides. So the topic for the rest of the talk, I guess, is computational complexity. So again, this is more computer science than Python programming, right? So CISC121 is basically meant to be not just a programming course, but an introduction to some of the concepts in computer science. One of the big topics in computer science, one of the more theoretical topics in computer science, is something called computational complexity, right? And so complexity is concerned with describing how many resources you need for our purposes to run a function, right? So you've got some function somewhere, right? And you want to know how many resources do I need to run this function, right? And by resources, we basically mean either time. Time is what we normally is what most people are concerned with, right? So you want to know how long will this function take to run, right? And really what you're concerned with is if I have some really big input, right? So I'm trying to solve a really big problem. How much time is this function going to take to run, right? And you might have several different alternative functions, right? So there might be several different ways to solve this problem. And what you want to know is, for large problem sizes, which one of these is fastest, right? Or are they all the same for large problem sizes, right? More or less all the same, right? So normally our resource is time. Sometimes your resource is memory. So especially people who work in mobile environments or embedded environments. An embedded environment is something like a computer that runs in your car, right? It's basically a tiny little computer that's got a small amount of memory. And it's basically a custom computer. And your modern car has roughly 100 or more of them sitting inside the car somewhere. Then your resource is also, you're also concerned about how much memory is this function taking, right? So we need some way to measure this, and that's what complexity is about. Usually complexity is expressed as some function, right? So you're going to write this as a function, and it's going to be a function of the input size it's going to be a function of the size of the problem, right? We've already talked about recursion a little bit, and in recursion we talk about the size of the problem. It's the same thing, right? So the size of the problem, it's always some non-negative integer value, right? So it's a natural number. There is a technical definition for the size of the problem. We're not really worried about that. In fact, you don't even really worry about that in the third year course, right? The third year course is CISC365, which is algorithms, right? Even in algorithms, you normally don't you normally don't define the size as the number of bits, right? That's the technical explanation. The technical definition of the size is the number of bits needed to specify the problem. But that's more precise than we need for most problems, right? So most of the time, we're going to define the size in terms of quantities other than bits, right? So you might have a list, right? You might have a function that takes in the list. So you might want to sort a list, or you might want to search for something in a list. We'll say that the size of the problem then is just the size of the list, right? So how many elements are in the list? We saw in the power of 2 problem, right? The input was an integer. So normally the size of the input is the size, or is the magnitude of the integer, right? And usually you're only considered with the inputs that can change in size, right? So for example, again, if you're going to sort a list, right, the size of the list can change, right? So sorting a list, and so that becomes the size of the problem. Okay, so I want to search a list, right? So I want to write a function that works with the list t, right? and I want to know, does T, right, does T contain that value, right? So does the list 0, 1, 2, 3, 4, 5 contain the number 6, right? And so there is a Python method in the list class that will tell you. Actually, you use, yes, actually you just use in. So there's an operator that will tell you, right? But if you were to write a function yourself, you would do something like this, right? You would write a loop, right, that looks at every element in the list T, right? Inside the loop, you would check, right, is T, oh, hey, I forgot, this was, sorry. Did I not fix all of these? No, this one slide. Sorry, I was doing this last night and I fixed them all except for that one, I guess. Okay, so write a loop over all the elements in the list, right? If an element is equal to the value that you're searching for, you know the answer is true, right? So you just return true and that stops the loop, right? Otherwise, after the loop, right? So we get to here, every element in the list, we haven't found val, so you know that val's not in the list, you return false, right? And so there's your little function that searches a list for a value, right? Now I want to estimate the complexity of this function, right? So in other words, I want to know how much time does this function take to run, right? Now, it shouldn't surprise you if you look at the function, right, that the time it takes this function to run is proportional to the size of the list T, right? It's obvious, right, because you're running a loop over all the elements in T, right? So if you double if you double the length of the list, you probably double the length of the time. You probably double the amount of time, right? So that should be obvious to everybody, I hope, right? To do this in a more formal manner, the way you do this is you look at your function, right? And you look at every line of your function, right? For every line of the function, you count the number of elementary instructions in that line of code. And I'll explain what an elementary instruction is in a second, right? After you've counted up all the instructions, you then ask, or you then determine, so how many times does this line of code actually run, right? So when I run the function, does this line of code run once? Does it run 0 times? Or does it run, say, n times, for example, right? And then to get the total number of elementary instructions, right, you just take each line of code, right? Look at the number of elementary instructions and you multiply it by the number of times that line is run, right? And then you just add everything together. So let's do this example. Well, first, what's an elementary instruction? Right. So an elementary instruction is any expression that can be computed in a constant amount of time. Right. So in other words, if it doesn't depend on the size of the problem, then it's an elementary instruction. Right. So if you declare a variable, right, so you say x equals something, right? In Python, that's an elementary. We will consider that an elementary instruction. Right. Assignment. Also an elementary instruction. So if I have another variable, if I have an existing variable and then I reassign the variable a value, that's elementary, right? It takes a constant amount of time. For our purposes, arithmetic is constant time, right? So that's elementary. If you're going to compare stuff, elementary instruction, right? Or and not elementary, right? The if, so when you write if blah, right? That takes just the if part and the else part, or the else if part, those are elementary. If the if part has a condition, the condition may or may not be elementary, right? Usually it is, but it might not be. So I'll explain that in a minute. If you need to access an element of a list or string, one element of a list or string, that's constant time. So that's an elementary instruction. And finally, if we have a return statement, that's also an elementary instruction. Now, loops are technically more complicated. Okay, so when you have a loop like for or something, technically the loop takes some time to set up, right? So if you write for I in range something, Python has to make a range object and assign that to your loop variable every time, or assign an element from the loop variable every time, right? So technically, there's more than one elementary instruction going on there. But we're just going to consider the for something to be an elementary expression, an elementary operation, sorry. Right, so when you see the for blah, we're going to assume for now that takes 1 unit of time, right? Again, if the blah, right, if the something involves something that depends on the size of the problem, it may not be an elementary expression, an elementary operation, sorry. Okay, so let's look at the contains example, right? So the first thing I want to do is I want to look at every line of code and count the number of elementary operations, right? So here's our for, right? I just told you a second ago that we're going to consider that to be one elementary operation, right? Next line, we have an if statement, right? So the if part here, that's one elementary operation. The comparison, that's a second elementary operation, right? So there's actually two operations going on here, right? You need to do the comparison, and then based on the comparison, Python has to decide whether it's going to go here or whether it's going to go back up to the top of the loop, right? So that if part we count as one, and the comparison we count as one. Return true. So a return statement takes one operation, right? There's no expression, there's nothing here that involves either a function call or some sort of arithmetic or something like that. So that just takes one operation, right? And then return false, right? Again, return statement, nothing here that involves any sort of computation. So that's just one operation there as well, right? So we got a total of 1, 2, 3. Yeah, so 1, 2, 1, and 1, right? So that's the number of elementary operations in each line. So that wasn't terribly hard, I hope, right? It turns out even if you get this wrong, so if you're off by 1 or 2, it doesn't matter in the end, right? So if we had counted this thing here as 1, right? You'll see shortly that it doesn't affect the final answer. Okay, now for each line of code, you want to count how many times does that line of code run in the function, right? So here's, again, the for loop's a bit sketchy because it's not exactly true that this runs once. Because the for loop does a for loop, there's a bunch of stuff that's not hidden, that's hidden from you that happens right here. We're going to ignore that for now, right? And we'll just say that that for statement here runs once, right? So that part of the for statement runs once. The stuff inside the for statement, right? That's going to run more than once. Okay. Return true. That only runs once, right? It doesn't matter that it's in the loop, right? So it's inside the loop. You might say, hey, doesn't this run n times? The answer is no, right? Because when you return something from a function, the function stops, right? So at most, it can run once, right? Even though it's inside the loop, right? At most, that statement runs once. Similarly for return false, right? At most, that statement can run one time, right? Again, because the return statement stops the function. The problem is this guy right here, the if statement, right? How many times does the if statement run? Well, suppose I have a list 0, 1, 2, 3, 4, 5, right? And I want to know, is the number 0 in the list, right? So 0 is the first element of the list. So in that case, that statement runs once, right? I have the same list, 0, 1, 2, 3, 4, 5, and I ask, does the list contain the value 6, right? And that statement there runs 6 times, right? Once for every element in the list, right? So 0, 1, 2, 3, 4, 5, right? 6 times, right? And so that statement will run n times, right? Where n is the number of elements in the list, right? On average, right? So if you tried to average out all possible lists and all possible values of val, right? Then that if statement probably runs roughly n over 2 times, right? So roughly, on average, if it's in the list, it's somewhere halfway in the list, right? So on average, that would be something like n over 2, something like that, right? And so there's a problem. I can't write down a number here, right? I can't write down the value for question mark, question mark, question mark. Oh. So how many times that runs depends on t, and it depends on val, right? Okay, so to get around this problem, right, we often consider what's called the worst case scenario, right? So the worst case scenario is, so the worst case scenario for the contained function is that val is not in the list, right? So if val is not in the list, you have to look at every element in T before you can say, oh, val is not in the list, right? So that's the worst case complexity, right? The greatest number of times that line has to run, right? Similarly, there's a best case scenario, right? So the best case scenario is when val is at the front of the list T, right? In that case, it only runs once, right? And then there's the average case scenario. The average case scenario is very hard to deal with in most cases. It's very hard to deal with in the general case. Normally, the best case scenario is not that interesting, right? Because normally your in this case contains the if statement only runs once, right? Normally, what we're concerned with is the worst case scenario, right? And so what that basically means is that if a line can run, right, then assume that it always runs, right? So here, when you do the worst case analysis of this function, you're going to assume that that line runs, right, for every element in T, right? So in other words, I didn't make a slide here. Oh, here we go. Here, right? So in the worst case, right, so now this has changed, worst case number of times run, right? That line will run that many times, right, for every element in T. And length of T is just the size of the problem, right? So length of T is the size of the problem it contains, right? And normally, right, it's very common that you see the symbol n used to indicate the size, right? So we're going to write n here, right? And this is the worst case number of times every line of this function will run. Okay, part 2, right? I now multiply the number of elementary operations by the number of time each line runs, right? So one elementary operation, the line runs once. 2 elementary operations, in the worst case, that line runs n times, right? 1 elementary operation, that line runs once. 1 elementary operation, that line runs once. Okay. Add everything together. So that's 1, 2, 3 plus 2n, right? So the running time for contained is some function f of n, and that's equal to 2n plus 3, right? And that f of n, it's sometimes called t of n, is called the timing function for contained, right? Okay, so I mean that wasn't terrible to do, I hope, right? You're basically trying to identify the elementary operations and figuring out how many times each line of code runs, right? Now, the reason you want to write down a timing function, or the reason we study these timing functions, is because you can implement contains in many different ways, right? So let's look at a slightly different version of contains, right? So in a slightly different version of contains, I'm going to use a variable called result, right? And I'm going to return the value of that variable at the end of the function, right? So in other words, I'm not going to return from inside the for statement, right? So I'm going to assume that the answer is false, right? Then in the loop, right, if I find val somewhere in the list, I'm going to set result to be equal to true, right? Once I've found a true value, I can break out of the loop, right? So I'm going to use a break statement here. If you go through that exercise of counting elementary operations and counting how many times each line of code runs, right, you end up with this, right? 1 operation runs once, 1 operation runs once, 2 operations runs n times, 1 operation runs once, 1 operation runs once, right? one operation runs once. If I get rid of the break statement, right? So if I remove the break statement, that would become one operation, but it runs n times, right? Because every time the if statement is, sorry, it could run n times in the worst case, right? Why can it run n times in the worst case? So suppose you have a list T where all of the elements are the same, right? So I have list T that's 1, 1, 1, 1, right? 4 ones. If I ask this, the list T contain 1, right? The result will be true for every element in the list, right? Remember, I'm removing the break state, right? So in the worst case, it's possible for this to be 1 times n, right? Where and that happens when you have a list where every element has the same value and you're searching for that value, right? That's why you want the break statement. You don't want the extra n here. If you add all that up together, you get 2n plus 5, right? Which is a different number than 2n plus 3, right? If you get rid of the breaks, if you get rid of the break statement, it becomes 3n plus 4, right? And so you've got all these different versions of contains, and they all have slightly different timing functions, right? Even though they all do the same thing, right? So depending on how you write contains, you can end up with different timing functions, right? Okay, that's fine. So that's contains too. Okay, so when you're counting the number of elementary operations, right? We just assume that every elementary operation takes the same amount of time, right? In other words, they all take 1 unit of time, but that's not true, right? It's not true on a modern computer anyway. So for example, if you add 2 integers together, or if you add 2 floating point numbers together, that's actually faster than if you multiply or divide 2 floating point numbers, right? And even though, so we're counting all these operations as elementary, saying they take 1 unit of time, but in practice, elementary operations don't all take the same amount of time to run, right? And similarly, it's not exactly clear, sorry, yeah, so, right, so all the different elementary operations might actually run in different amounts of time, right? What we're concerned about, though, is whether or not the elementary operation runs in a constant amount of time, right? So that's what defines an elementary operation. So when you're actually counting up the right, and so when you're actually writing down this expression, right? So when you go through this exercise of counting how many elementary operations there are and how many times they run, right? Those constants 2 and 5, they're probably not going to be entirely accurate, right? So what we want is some way to compare different functions, to compare different implementations of a function, right? So different implementations of contains. We want to be able to compare them in some way that doesn't depend on these constants 2 and 5, right? So the notation that lets us do this is something called big O notation, right? So big O describes the complexity of an algorithm that's insensitive to variations in how you counted those elementary operations, right? So if you, right, so if different elementary operations take different amounts of time, right? In other words, these 2 and 5, they're not entirely accurate, right? I still want a way to be able to compare different implementations of contains, right? Where this stuff, right, where the inaccuracy in the 2 and the 5 and in how you counted how many operations there are doesn't matter, right? So if we use big O notation, we would say that the complexity of contains is in big O of n, right? So it's always big O round bracket, something inside the round brackets, right? So big O is just a function. Mathematically, that's the definition. Don't worry about it, right? For 121, you don't care about the mathematical definition, right? But that's what it is if you're interested. Okay, this is what's important in 121, right? So if someone tells you the complexity of contains is in big O of n, right? What you need to know is that it means that, So big O notation, so big O of n means that for large values of n, right? So for very large values of n, really what it means is as n approaches infinity, right? The number of elementary operations required by contains, right, is less than some constant times n, right? Go back to the mathematical definition. You can figure it out, right? The constant here is big M, right? So all this is saying here is that 2n plus 5 is less than some constant times n, right? So if you pick a constant, 2n times 5 is definitely less than 3n, right? If n is big enough, right? Because the 3 is bigger than the 2, right? And the plus 5 is not going to matter for large values of n, right? So that's all it's saying, right? The number of elementary operations is less than some constant times n. Okay, so how did I go from 2n plus 5 to n, right? And you get all the mathematical details and data structure. So CISC235, if you continue in computing, and or algorithms, so CISC365, right? So it's explained to you how you get these things. You might also do it in one of your first year courses. First or second year courses. You might do a little bit of it, right? Again, we don't care about the we're not concerned with the mathematical derivation in CISC121, right? And so you can just use these simple rules, and the rules you can derive once you understand the mathematics of the of big O, right? So if your function is a sum of several terms, right? So 2n plus 5, right? That's the sum of two terms. Then you keep the term that grows the fastest, right? So 5 doesn't grow, right? 5 is just a constant, so it never grows. So we keep the 2n, right? If you have some polynomial in n, right? So n squared plus 3n plus 1, right? Then you keep only the term with the highest power of n, right? So in that example, you would keep only the n squared, right? Because the n squared grows much faster than n, right? For large values of n. Okay, so after step 1, you've got one term left in your expression, right? So if that term is multiplied or divided by a constant, then you just throw away the constant, right? So if fn is 2n plus 5, right? I keep the 2n, and then I throw away the 2, and that's how you get the n, right? So here's some examples, right? So 2n plus 5, it's the sum of two terms. Keep the term that grows the fastest, that's 2n. Now discard the constants sitting in front of the n, so that's just n, right? 3n squared plus 100n plus 21, sum of three terms, right? Keep the term that grows the fastest, so that's 3n squared, right? The 100 here doesn't matter, right? You might say, hey, look, 100n, that's a lot bigger than 3n squared. That's not true if you plug in a big value of n, right? If you plug in some big value of n, then 3n squared grows faster than 100n, right? Even if that thing there was like a billion, eventually 3n squared becomes bigger than a million n for some large value of n, right? If you want to keep the term that grows the fastest, we keep the 3n squared, right? It's got a 3 in front, so throw away the constant, you get n squared, right? 2 to the power n plus 15n. 2 to the power n grows faster than any n raised to a constant power, right? So n to the k, where k is a constant, is always smaller than 2 to the n, right? For some big enough value of n, right? So 2 to the n is the term that we keep, right? That's not multiplied by anything in front. It's not divided by anything, so we don't throw anything away, right? So that becomes big O, 2 to the n. Finally, that's about as complicated as an expression as you can expect to see, even in CISC235, actually, probably even in CISC365, right? Here we've got n times log n, 9 times log n, and a 3, right? N times log n grows faster than log n, right? Because n times log n is equal to the second term times n, right? So that's the term that we keep, right? It's multiplied by 12, so you throw away the 12 and you end up with n log n. So it's not difficult to go from f of n to O of n, right? At least not in 121. Okay, so what does all this mean, right? So remember, this is O of 1, O of n squared, O of 2 to the n, O to the n log n, right? What does all this mean? Well, these function values that go in here, right? So they all define what are called complexity classes, right? In other words, they describe families of algorithms that have the same complexity, right? So O1, that describes an algorithm that runs in constant time, right? So in other words, these are the elementary operations, right? What does O1 mean? It means, right, the runtime of your function does not depend on the size of the input, right? So if your function takes in a list, it doesn't matter if the list has 1,000,000 elements or if it has 1,000,000,000,000 elements, it takes the same amount of time, right? So what are examples of things that run in constant time? Well, if I want to know if an integer is even or odd, right, that's constant time, right? You just compute the remainder after dividing by 2 and check if it's check if it's 0 or not 0, right? That takes a constant amount of time. List indexing to get one element or string indexing to get one element, right? That takes a constant amount of time, right? So it doesn't matter how big the list is, it doesn't matter how big the string is, it's going to be a constant amount of time. If you can use an algorithm or a function that's O1, you want to do so, right? Because you know that it always takes a fixed amount of time. Okay, O log n. So this is a different complexity family, right? So it's different than O1, right? So it describes a different family of algorithms. And it describes the family of algorithms whose runtime grows in proportion to the logarithm of the input size, right? Now, I wouldn't, unless you're really mathematically inclined, I wouldn't describe it in those terms, right? Instead, think about it this way, right? If I double the size of the input, right, then your runtime increases only by 1 unit of time, right? So think about that. So I have a list of size 1,000, and I double it. So it's a list of 2,000, right? And the amount of time I need increases only by 1 unit. That's what log n means, right? So in other words, the runtime grows very slowly, right? If you can use an O log n algorithm, if you don't have an O1 algorithm, right, but you do have an O log n algorithm, use the O log n algorithm, right? It's very fast, right? So this is called logarithmic complexity. And an example that we'll see, I think next week or the week after, right, is if you're searching a list, but the list is sorted, right? So I have a sorted list, for example, like an English dictionary, right? Then you can efficiently search that list using an O log n algorithm, right? And we'll see exactly how you go about doing that, right? That's binary search for those of you who have heard of that term before. ON. So ON describes an algorithm whose runtime grows in proportion to the size of the input, right? So that's contains, right? In other words, if you double the size of the input, you roughly double the amount of time it takes to run, right? And that's linear complexity, right? So example, right? If you search an unsorted list, so for example, contains, that's ON. If you're looking for the minimum or maximum in a list, that's also ON. Right? Because to determine the smallest or largest value in an unsorted list, you have to look at every element in the list. Okay, n log n. So that was one of the examples that we saw earlier. That describes an algorithm whose runtime complexity, it's slightly more than linear, right? Now you're taking a linear algorithm, but you're multiplying it by log n, right? So what does that mean? Well, that means if you double the size of the input, right, it slightly more than doubles the runtime, right? So it's not quite double, it's a little bit more, right? And this has the name linear arithmetic, but it's not very common. That's what it's called, right? This family of algorithms is important because efficiently sorting an array or list has this complexity, right? So if you have an unsorted list and then you sort it with an efficient sorting algorithm, that algorithm probably has O log n, n log n complexity. Right, and, n squared. So n squared is an algorithm whose runtime grows in proportion to the square of the size of the input. Right. Again, I wouldn't think of it in those terms. Instead, if you double the size of the input, that quadruples the running time. Right. And so this is called quadratic complexity. Not surprising, right? You got something squared. Right. There are lots of n squared algorithms. If you have two nested loops, it's probably n squared. Right. If you have three nested loops, it's probably n cubed. But we'll look at that. We'll look at examples of those later. If you inefficiently sort an array or list, right? Most of those inefficient, sorry, not most. Many of those inefficient algorithms are in n squared, right? N squared is worse than n log n. If you have two lists of the same length, and you want to know is everything in the first list also in the second list, right? That's n squared. If you have two matrices, right? So hopefully you've taken linear algebra. If you have two n by n matrices and you add them together, right? That takes O n squared time, right? Because there's n squared elements, right? You have n rows, n columns. You have n squared elements in the two matrices. To add them all together, you need O n squared operations. Okay, last one. O to the 2n. These are uncommon in CISC121, but you will see some examples at the end of probably in week 11 or 12 that have this complexity. So O2 to the n is an algorithm whose runtime grows exponentially, right? What this means is if I increase the input size by 1 unit, you double the runtime, right? So every time the size of the problem gets bigger by 1, the runtime doubles, right? If you think about that for a minute, right, you'll quickly realize that these are very, very, they have this is a very, very high computational complexity, right? So this is exponential complexity. The most common example that I think most people would be familiar with is if you have a combination lock, right? So you got one of these locks that's got like 4 or 5 dials on it. If you try to open the lock by trying every possible combination, that's exponential complexity, right? So if you have 5 dials that have the digits 0 through 9, right? There are 10 to the 5 different combinations, right? And so, right, so trying every possible combination by hand is very slow, right? And every dial you add increases the number of combinations by another factor of 10, right? And so that's O to the 2n. You want to avoid these functions if you can. Unfortunately, lots and lots and lots of important computational problems have this complexity class. Okay, so if you were to plot these functions, right? So if I'm just plotting n, right? I'm plotting n log n. I'm plotting n squared, and I'm plotting 2 to the n, right? You can see how fast these algorithms are. You can see how these algorithms grow in comparison compared to one another, right? On is a straight line, right? Constant time would be here. It would be the x-axis, right? So a constant time algorithm would just be horizontal. When is here. Here's On log n, right? At this scale, that almost looks like a straight line. It's not quite a straight line, right? It is slightly curved. N squared, you can see takes off like this, right? And you can see that n squared is much worse than On, right? And finally, O2 to the n, you can see is much worse than all of them, right? So for O2 to the n, that function grows very quickly as a function of n, right? So when you have a bunch of different algorithms and someone tells you the big O complexity of all of them, right? You want to choose, typically you want to choose the one that has the smallest or the best complexity, right? So if someone gives you a choice between an On algorithm and an On squared algorithm, you typically want to choose the On algorithm, right? Okay, and so that's complexity in a nutshell. It's the book tries to do complexity in a very hand-wavy sort of way. And so the other way to do this is to do this in a very mathematical way, right? So the other way to do this is to throw this at you, and then to try to explain complexity using that. I've tried to split the difference and go halfway in between, right? So hopefully that gives you some appreciation of what complexity means. The next assignment, you'll have to do a few small exercises where you're estimating complexity of algorithms, right? Yeah, so for now, review the material in the in this session, and read the textbook. So the textbook's not a bad introduction to it, to complexity, but it doesn't quite go into enough detail. All right. Does anybody have any questions about complexity? Mackenzie?
My question was actually about it was a comment on the self-assessment quiz.
Okay, hang on. So let's not deal with that yet. I'll deal with that in a second. Is there anybody else who want to ask anything about complexity? No? Okay. All right. So Mackenzie, you want to ask about that self-assessment?
Yeah, just a comment on the humidity equation that was given. It didn't include the air temperature.
Hang on. What do I want? Whoa. On here. 120. If you haven't seen it yet, it's here, right? It's under assessment, self-assessments. Oh wait, I have to. So, yeah, I don't see the same thing. You guys have to preview. Okay, so given, did I screw it up? Oh, hey, something's missing.
Yeah, the air
Where's
temperature.
The air temperature? Oh, the air temperature is missing. Okay, I have to fix that question. Yeah, I'll fix that shortly.
Okay.
Thank you.
I've actually got another quick question about this self-assessment on question 4. Well, actually, first I wanted to clarify, when you were mentioning that there was a question 4 where you changed an output, was that in relation to this or the assignment?
That's the assignment 3.
Okay, because I have a question about this 4 too. When I take the answer and put it into idle, I end up getting an error, and I wanted to just clarify if this was the right logic.
I get an error? Sorry.
It also could definitely be on my part. So.
No, that's fine. For val in A. Okay, so what's the you get an error. Okay, so what's the error that you get?
I believe it's the list is out of range.
Oh, okay, let's take a look.
Yeah, and whether or not it produces an error, I do have a question of the logic.
Statements. Oh, that's embarrassing. So this is I gave you a sample input, right?
Yeah, you did.
It barfs on the sample input? Oh, hey, that's embarrassing. Sorry. Okay, so what did I do?
That's okay. I guess the question is, your first line is taking M max A.
Yeah.
And I was wondering why we're not taking the length of that list rather than the maximum.
It's because okay, so suppose I gave you the list with just 100 in it.
Right.
Okay. So the histogram is supposed to return a list whose ith entry is the number of times the integer I appears in the argument. Oh yeah, that's the problem. It's I plus 1. Okay, so whose ith entry is the number of times the integer I appears in the argument array, right? So if I have a
Sure.
list with just 100 in it, right, then the 100th entry should have a 1 in it. So in other words, there should be 101 elements in the list. Ith, 0th, yeah, because there's a 0th entry, right? Oh yeah, I guess it depends on how you interpret ith.
Yeah, I actually see what you mean now, picturing what
Yeah.
a histogram was. But
Yeah.
anyway, yeah, thanks for that explanation.
Okay, that should be +1.
Okay, cool.
Well, that was dumb. Sorry. And there you go. Right. Yeah, that should be +1.
Great, thanks a lot.
Okay. If I fix that, how does that work? If I fix Onju is really weird. I think with the self-assessment exercises, if I change them, you'll see the change. If I do a quiz and change the answer in the quiz, you won't see, and you've already gotten the quiz back, you won't get the answer. You won't be able to see it. It's very weird. Okay, does anybody else have any other questions? Anybody? I think that fixes it. Yeah, okay. All right, if there's no other questions, that's it for today. I will, don't forget that you have a quiz tomorrow. I will be here during office hours, so you can still ask questions tomorrow during office hours. And other than that, I will see you again next week. Thanks, everybody.